Welcome to Data Mining Module 1, Topic 1, What is Statistical Learning? In this topic, we're going to talk through some fundamentals of statistical learning and data mining. So data mining and statistical learning are primarily concerned with what's called the prediction problem. So let's walk through two examples of the prediction problem. Our first example is going to be displayed on this axis here. So let's suppose I have some data with some x values, which are going to be our inputs, and our y values. And the goal of the prediction problem is always to predict the output values based on inputs. And so let's take, for this example, x values being square footage of a house and the y values being the price of the house. So I may have some houses that sold, and I know the square footage and price for the houses that have been sold. And so I can plot them on my axis something like this. So I may look at these plots and decide I can model this relationship with the inputs and the outputs with a line, which I'll draw in red. So that may give me one model for this way to predict the outputs based on the inputs. Or I may decide a line that looks like the one that I'm drawing in green is really a better fit. And so there's a lot of reasons I may choose the red line over the green line, right? If you'll notice, here's for example, houses with large square footage, the amount that the price goes up doesn't increase linearly with the square footage. This may be true, particularly if there's houses with large square footage in my area that tend to be older houses that have a less of an increase in price. And so there may be something impacting that goes along with those square footages that impact the price of the house. So there are a lot of reasons to pick the red or the green, and based on the data that I've plotted here, either the red or green could be a reasonable model or just picture that gives us a relationship between the inputs and the outputs. This relationship, this model that we're talking about here is a regression problem. And in the regression problem, the outputs are continuous valued variables like price. Now there's another type of problem that falls under the title of prediction problems that we're going to talk about. And for this example that we're going to walk through, suppose we have two different variables that we can measure, x1 and x2. And so for the example, let's walk through. Suppose we're taking a dog and we're going to measure its ear length and its leg length. And we want to tell if that dog is a basset hound or a shepherd. Now, basset hounds tend to have shorter leg lengths and suppose x1 is leg and x2 is the ear. So basset hounds will have shorter legs and longer ears. So our basset hounds might be well represented by the locations of these V's on my axes, where the shepherds have longer legs and shorter ears. And so my shepherds may, if I plot their ear and leg as scatter plots and label them with S's on these axes, go where I've written the S's. Now, if I want to model the relationship between legs and this label, either basset hound or shepherd, that goes with the pair of measurements for the leg and the ear, I might draw a line on my axes right there, like what I've written in red, and say anything above that line is likely to be a basset hound, and everything below it is more likely to be a shepherd. Or I might draw a green line that fits the contours of our measurements like this. And so maybe that green line is a better relationship. Just looking at the data, it's hard to tell whether the red line would be better or the green line would be better. This is sort of the glorious, fun, beautiful part of data mining, is trying to figure out how much I want to customize my model to the data. And so this type of prediction problem that we're talking here on the right-hand side is called the classification problem. The difference between regression and classification: in regression, our y values are a continuous set of real numbers. So this script R that I just wrote, that stands for the real number line. In the classification problem, y takes on its values in some discrete set. In this case, y is in the set that includes the letter B or S, or the label Basset Hound or Shepherd. So this is the main goal of the prediction problem, is to determine this relationship between the outputs, the Y, and our inputs, which are X's. We can't exactly determine this relationship, and it's a relationship, not a function, because sometimes you're going to have different outputs for the same input, meaning you might have two different houses that have the same square footage but have different prices. We don't want to call this a function. It's a relationship, but we're going to approximate it with a function. So this is really the main goal of data mining, is to approximate this function, and we write this function y hat equals f hat of x. We put the hats on there. That refers to these red and green lines that we drew that are going to approximate the relationship. And so the model is this function that we're using to approximate this relationship. And the way we train the model is to estimate this f hat, this function, based on the training data. So the training data would be my sets of S's or B's in the right hand, or the set of houses that have sold that I know their square footage and their price on the left-hand plot. When dealing with training a model for a prediction problem, there's a couple of types of errors that can come in, and this helps us describe and understand what types of errors we're causing, and helps us understand, should we choose a model that's more like the green curves that we've shown here, or more like the red lines. So one of the types of errors that can come into play are called bias errors, and these are errors that are caused by erroneous assumptions in the model structure. So the red curves that we've drawn here, they're drawn with the assumption that the relationship is linear, meaning on the left-hand side it's a linear function between the inputs and outputs, and on the right-hand side we can separate the Bassets from the Shepherds with a linear separation line. And so we say this type of model drawn in red has high bias, right? And in a sense that means even before we started training the model is biased towards assuming that there's a linear relationship. A high biased model will tend to be in danger of having high bias errors. Now, if the data fits the bias of the model, meaning if our relationship really is linear, then we're not going to have those bias errors. We would want to use a model that assumes the relationship is linear if the relationship really is linear. The other type of error we can have is what's called variance error. And variance error is caused by sensitivity to small fluctuations in the training data. So this green curve represents a model that we would say has high variance, right? Because it will alter itself to change small fluctuations in the training data. So one of the grand strategies in data mining is to try to minimize errors from bias and errors from variance at the same time. And there's a number of ways you can do that. And a lot of this course is going to be talking about what are the different ways we can do to model relationship between inputs and outputs, and then how to reduce both bias errors and variance errors. One of the problems that we have to deal with, and it's a really good terminology for having this, for this problem, is called overtraining. Overtraining is when we've trained a model to follow attributes in data that are not generally valid. So, for example, in regression, if I chose the green model and I said, oh, as houses get larger, they don't tend to gain as much value for their size. If I added a bunch more data and I didn't see that trend to continue in the data, then I would say that model is overtrained. Other terminology that we're going to want to help us understand this relationship between models that are higher variance or higher bias, there's parametric models, and these are models that have a predetermined formula. So like the example that's up here, f hat, that's a linear formula. It's beta 1 times x plus beta naught. And in parametric models, training the model consists of determining those parameters that are going to go into the model, hence the name parametric. In non-parametric models, those are models that do not have a predetermined formula. And as you might imagine, parametric models tend to have a higher bias because there's a predetermined formula that tells us the structure. Non-parametric models This is a tendency. This isn't always true, but generally will have higher variance because they'll be more able to customize themselves to the data. Okay, so let's talk about some terminology. The basic goals we talked about in data mining is to predict outputs from input values. The inputs are sometimes called predictors or independent variables or features. Output values are sometimes called responses or dependent variables. There's three different goals that we might have in data mining. You can put data mining goals in these three categories: statistical inference versus prediction versus causality. So statistical inference is just inferring some relationship between our variables. Prediction is the process of determining outputs from inputs, or training a model that will model the relationship between the outputs and the inputs, so that in the future, if we have further examples of inputs, we can use our predictive model to predict what the output values should be. The third process that we have on this list is causality. We have causality on this list most importantly, so we don't actually think we're doing causality when we're talking about either prediction or inference, right? Even though we can predict values for y based on x, it doesn't mean that x is actually causing y to occur, right? So there's rare cases, maybe if we're looking at data off a sensor that's monitoring a physical process where we know some chemical reaction is occurring that causes y based on x, but other than those rare cases, we want to avoid talking about causality. So our relationship between x and I doesn't mean that x is causing y. A little bit more terminology. We've talked about regression, which is the prediction problem when we're determining outputs that have continuous values, and classification, where our outputs have a class label. Other goals that come up in data mining, there's something called unsupervised learning or clustering, which is grouping our data not based on output labels that are given, but just based on similarities in the data. There's also a process called target detection, where we're trying to detect one single class. It's a subclass of the classification problem, where we're trying to detect one specific class in, for example, trying to detect patients with cancer. So it's cancer that we're trying to detect versus non-cancer. So target detection often has a slightly different approach. And then anomaly detection, where we're just trying to find rare, but we're not sure why they're unusual, but things that are unusual. So we've talked about training data. Training data is the data that you create your model from, and then there's test data, which you often use to test your model to see if it generalizes to data that hasn't been trained on. Related fields, there are a couple of related fields that we should talk about that you should be aware of that are very similar to data mining, and that are often used interchangeably with data mining, but often have a little different emphasis. So first field worth knowing about is machine learning. When people say machine learning, they're often talking more about putting an emphasis on creating data mining algorithms and then implementing them on computers. So it's more about a little more focus on the computer implementation. When people talk about statistical learning, and our book is a statistical learning book called An Introduction to Statistical Learning with Applications in R, there's an emphasis on the rigorous statistics underlining the algorithms or the methods or the models. And that's going to be a little bit of the emphasis on this course. We're doing data mining, but we want to have a rigorous approach to the models and algorithms that we're dealing with. You'll often see people talk about artificial intelligence. When they talk about artificial intelligence, there's often an emphasis on using the methods or the algorithms similar to data mining algorithms, but to have a computer make decisions, and then also to respond to some input. So having a car navigate and drive on its own, having a robot navigate a room, playing chess, things that are looking at possibilities and then having the computer take some action. Another field, knowledge discovery and databases, KDD. In knowledge discovery and databases, there's an emphasis on the database that's the algorithms are being applied to. There's a focus on data cleaning or other things that you would do with databases specifically to get your information. Data science is a field that involves three components and then doing all three components together. So there's doing the data mining or statistical learning algorithms together with some domain expertise in the area where the data is coming from. as well as computer expertise to properly implement the data mining methods on a computer with a good architecture. Last related field on our list here is signal processing. Signal processing often has to do with signals from sensors where there's a background noise, and that's assumed to be a Gaussian noise, and then you're trying to find your signal out of that noise. So let's talk a little terminology about data. So data consists of observations and features. And so here's an example data set. So we have 3 people, Bob, Mary, and Joe, and we've measured their height and their weight and their state that they came from. So when we say observations, we mean these observations for these individual people. So Bob, we measured his height and his weight, and he's told us what state he comes from. That's one observation. Mary, with her height and her weight and her state, is another observation. When we talk about features, we talk about these different variables. Height is a feature variable, weight is another feature variable, and the state they came from is another feature variable. So some characteristics of data. We have the dimension of the data, that's the number of features. We also have the different variable types. So our feature variables may be of different types. It might be what we call qualitative, which is categorical or discrete or factor variables. And those are variables that have a finite number of distinct values. So here our state is Arizona, New York, and Virginia. Those are examples of qualitative or categorical variables. Our variables can also be quantitative or continuous. So here height and weight are continuous variables. They can take on any number in a range of numbers. The last type of variable that we'll come across is ordered categorical variables. So small, medium, large. So these are discrete variables that have some specific order that has meaning to them. So let's talk about a few examples of learning problems just to flesh out the discussion that we've had today. So we may want to predict housing prices based on information such as size, age, square footage, and neighborhood. This is a regression problem, kind of the standard first regression problem people see. We may want to predict whether a patient will develop complications based on demographic factors and clinical measurements. This is a classification problem with just 2 classes, develop complications or not develop complications. We may want to predict a person's music preference based on preferences on past songs. So if you play a streaming music service that provides you with music on the go, that's likely that music service is doing this type of problem here. This is a classification problem, or at least we could call it a classification problem. It has many classes. So the next song that you might get recommended, there's maybe 10,000 different songs that they could recommend and play for you, and so the computer has to determine which of those 10,000 songs is best based on your previous preferences. Last type of problem for us to go through our example list here is determining whether an increase in police function will lead to a decrease in crime. So this is more of a statistical inference function, and probably one, if somebody talks about it, you'd have to be careful to avoid talking about causality. Okay, so let's review basic terminology we've talked about. We've talked about the prediction problem, which means we're estimating this function f hat that's supposed to approximate a relationship between inputs and outputs. We've talked about this prediction problem can be a regression or a classification problem. We've talked about what input variables and output variables are, and then we've talked about examples of data mining problems. Thank you very much. Look forward to seeing you in the next topic.